So we've got some interesting series here to test for divergence or convergence. So for this first one here, we have the infinite sum from when n equals 1 to infinity of 3 to the n plus 2 to the n over 6 to the n. And the way to do this one is to use the comparison test. So what you can say here is that this series is less than the infinite sum from n equals 1 to infinity of 2 times 3 to the n over 6 to the n. And basically what you do is you replace this 2 to the n and say that 2 to the n, that exponential, is less than 3 to the n. So we're going to get this series here, which from here we can just say that this is equal to 2 times the infinite sum of n equals 1 to infinity of 1 over 2 to the n. And what this is this is a geometric series with the r value less than 1, which converges. So what we can say is that from the comparison test, since this series is less than a series which converges, our original series converges too. So that's that one. Number 2 here says the infinite sum from n equals 2 to infinity of 1 over ln n. And this is also going to be the comparison test, but we have to be a little bit sneakier here because there's no easy way of getting rid of this ln n. What we can do is, let's say we were to draw a graph of ln n, which looks something like this. And we got obviously our 0 at 1, 0. We could say that ln n is always going to be less than the function n. Let's say we're to draw that there. And of course on n, we're going to have the point 1, 1. So we can say that this series is actually greater than n equals 2 to infinity of 1 over n. Because n is always going to be larger than ln n, and it'll be, therefore 1 will be divided by a bigger number, which will make it smaller. So this series, our original one, is actually going to be bigger than the infinite sum from 2 to infinity of 1 over n. But we know that this is a divergent series if you do the p-series test. So what we can say then is that our original series diverges. Now this one here looks like a bit of a mouthful to take in. Got a lot of stuff going on. And you could try doing a few things. You can maybe try doing the ratio test, but that's probably a bad idea because you're going to have trying to cancel out like terms with trigonometric functions, which doesn't really work out that well. So what I would try doing here would be to use the test for divergence. So we take the limit as n approaches infinity of the general term an, which in this case is going to be n times 2 cos 1 over n minus sine 1 over n minus 2. Now this limit looks a little bit tricky, and there's a problem here because this is going to be an indeterminate form. We're going to have infinity times 2 cos 1 over infinity, which would be 0, which would then become 1 in the cosine. You get a bit of a mess here. And you could try doing stuff like L'Hopital's rule, like bringing this n to the denominator, making it to the negative 1. But I would say that an easier thing to do would probably just say let n equal 1 over u, or therefore that u would equal 1 over n, therefore. And we know that as n approaches infinity, u approaches 0. So this limit would instead become the following. It would become the limit as u approaches 0 of 1 over u times 2 cos u minus sine u minus 2. So I'll just write that with the u in the bottom here, with the limit as u approaches 0 of 2 cos u minus sine u minus 2 all over u. And so this is a lot easier to deal with just by making the substitution here. And now if we try to evaluate this, we'd say that as u approaches 0, 2 cos u is going to approach 2. But then we're going to be subtracting 0 and then subtracting minus 2. So we're going to get 2 minus 2, which would be 0. And then the bottom, u will approach 0. So we're going to get is a 0 over 0 type limit. And when we get this indeterminate form, since this is also differentiable, we can use L'Hopital's rule. So now if we differentiate the top and the bottom, we're going to see that this is equal to the limit as u approaches 0 of negative 2 sine u minus cos u over top of 1 when we differentiate u. And from here, this can be evaluated pretty easily. As u approaches 0, this will approach 0 here, the negative 2 sine u, and then the negative cos u will approach negative 1. So this limit will be negative 1. And using the test for divergence here, since this value is not 0, we can say that our original sum diverges. Say that just diverges. So those are some good series to test your knowledge of the comparison test and the limit test for divergence.